Greetings once again from Rescue Shuttle Control. We've noticed in our telemetry that you have succeeded in getting your lights turning on and off. And so that's great news because it means that you're well on your way to getting your systems up and running. We're going to continue working on today's session with learning how to construct circuits and control them with your Hero controller. And we're going to build on what we learned in the last session. So today, what we're going to do is try and give you a little more flexibility in controlling your lighting. We've noticed that some of your power levels are dropping, and you need to be able to turn those lights on and off when you don't need them. So, in order to do that, we're going to involve some switching in today's activity. We do have a switch as a part of our discrete components. You may have noticed this before. We have this little device that you can take a look at here. It's called a dip switch. And DIP is an acronym. DIP stands for dual inline plastic. And that name is sort of logical. You can see that it is, like many electronic components, in a little plastic package. And it has two rows of pins in line with one another. So that explains the name dual inline plastic. This particular device is a set of switches. You'll notice that there are actually 3 switches built into one device here. So we could, in principle, use this to control 3 separate circuits. Although today, we're only going to use one of them. Switch number 1, which you'll see is indicated with the 1 on top of the device right here. We'll soon find out that when the switch is flipped from the off to the on position, like so, then the pins on opposite sides in that row are connected and you have a complete circuit. So we're going to use that today. Now, the last time we worked with the Hero, we basically were controlling outputs. We were asking the Hero through the code that we wrote to either switch a high voltage or a low voltage to a particular pin as an output. We're going to continue with that today, but we're going to add an additional function today. This time, we're going to have the Hero not only controlling outputs on certain pins, but we're also going to have it accept input from us. And the input that it reads on whatever pins we specify will cause the Hero to take the actions that we program it to take. So we're going to add that additional function today, both in terms of the way we build our analog circuit and in terms of the way that we program and write code for the Hero. So let's direct our attention for a few moments to our breadboard and Hero and look at some of the circuit building that we need to do today. If you look at the upper part of the breadboard, you'll recognize what looks like a fairly familiar circuit from last time. You'll notice that we have a circuit that begins on pin 12, and you'll remember that last time we were able to ask the Hero to connect pin 12 to 5 volts when commanded. And so from that, we connect to a row on the breadboard. In this case, it happens to be also row 12. Wouldn't have had to be row 12, though. It could be any place we conveniently wanted to build the circuit. From that connection on pin 12, we pass through a current limiting resistor, and you'll remember from our discussion last time that we've chosen the value of this resistor to give an appropriate amount of current to light our LED light bulb. The current after passing through this resistor passes into the positive terminal of the LED lamp, and we've positioned it so that the current will come out of the lamp on row 11, just above there. Now, in order to complete the circuit, we're going to have to provide a return path back to ground. And so this green wire right here takes us around and down to a row on the column, rather, on the breadboard that's labeled with a blue line here. And then onward from that to ground on the hero. You might wonder, why didn't we just go directly from row 11 to ground? And we certainly could have done that, but we were anticipating that we're going to need to build another circuit in a little while that will also want to have 0 volts access or ground. And so we've chosen to make this entire blue column right here 0 volts by connecting it to ground on the hero. And then anytime we want to get 0 volts, we can connect to anywhere on that blue column. So far, that looks like a pretty familiar analog circuit to us. And all we need to do is ask the hero to supply 5 volts to pin 12, and our lamp should go on. Now, what we want to do in today's exercise is figure out a way of turning the light on and off without having to re-upload the program to the hero every time. And we're going to do that using this dip switch. Now, you might think that all we'd want to do is just take the switch and put it in series with the circuit that's carrying current through the lamp. And that would be one way to do it. But we want to have a little more flexibility in the way that we can control this. And so rather than directly interrupting the circuit and the current that's passing through the lamp, we're going to control the hero by supplying it with an input. So in order to see how we're going to do that, it's time now for us to switch our attention over to the code window and see how we're going to handle this. As we look at the code window, we'll see we have a couple of empty routines here, the setup routine and the loop routine, which we're about to populate with some code. We've also got a variable, LED, for our light emitting diode, that has been assigned our traditional value of 12. So when we identify LED as 12, it means that when we set the voltage on that pin high, the light will go on. Now what we're going to need is another variable. And this is going to be a variable that we will use to command the hero through our switch. And so what we're going to do is define another variable, and we'll name that one switch1. You'll notice that we have a comment next to this just to remind us that we're setting switch 1 equal to 2, which means that pin 2 will now be the pin on the hero that we're going to connect to our switch. Now, we have to ask ourselves, well, what are we going to do with that pin 2 that's different from what we did, say, with pin 12? And in order to understand that, we want to see what we're going to do in the subsequent setup and loop functions on our hero. So the next thing we'll do is place some code in setup and analyze what it's doing. You'll notice that our comment right now says that we're going to set up both an output and an input on the hero. We are now, once again, using pin mode. And in the first of these two statements, you'll notice that pin mode is very familiar to us. It's just like we used it last time. We're taking LED, which is 12, and we're setting its function to be an output, so that when we command it, we can cause LED, or 12, to be either high or low. In contrast, we're going to use pin mode to make switch have a function of an input. The hero is not going to cause input to change. Hero is going to watch that input and take cues from its value. so that when we cause input to change, the hero will take appropriate action. All right, so that's our setup. But now what are we going to do with that? Well, the real action is now going to be taking place in our loop. And so here's where we will see something quite different from what we have done before. So let's go ahead and put a block of new code into loop and talk a little bit about what it's doing. Got a couple of comments here. I'm making note here that within loop we're taking repeated actions, but these are now going to be actions that are based on the status of the value of switch 1. That is the voltage that is being applied to pin 2. Now, the next thing that happens in loop is something new. We're going to apply a conditional test. We're going to ask the hero to check what is the voltage on pin 2, or in other words, switch 1. If digital read of that switch of pin 2 is equal to high, then take the action contained within these curly brackets, which is our usual action of turning on the LED on pin 12. So in other words, set LED to high, so the light will go on. But now this is a conditional. It's only taking place if switch 1 is high. On the other hand, if it's not high, in other words, if it's low or 0 volts, then set digital write LED to low. In other words, turn the LED off. So what this means now is that depending upon whether or not switch 1 is high or switch 1 is low, you will either have the LED go on or off, and we can control that. All right, hopefully that's fairly clear. Our circuit on the breadboard is not quite ready to work with this code yet. We're going to have to set up a way of setting the value of pin 2, or switch 1, to either high or low, depending on what we want. So what we're going to do, returning over here to the breadboard, is take our dip switch and place it so that the first of the 3 switches, switch 1, is spanning across the gap here in the breadboard, so that when the switch is in the off position, these rows on the left are not connected with these rows on the right. But for example, if I take the switch and I flip it to on, like so, oops, let's get that switch on. Now you can see our first switch here is lined up with row number 23 on the breadboard. And now there will be a complete connection from the left hand to the right hand side of row 23. If I switch it back to off, then there will be no connection. Now, this is part of the progress that we want to make, but the next thing that we have to do is to provide a source of 5 volts that we can either connect or not connect to pin number 2, which is going to be our input to the hero. So here I have a long wire that I connected to 5 volts on the hero, and I'm going to bring it over here and connect it up to the right-hand side of row 23, like so. Now, with the switch in the off position, that's not going anywhere. There's no completed circuit, and the left-hand side of row 23 is still at an indeterminate voltage level. On the other hand, if I were to switch this to on, the current can now flow through the switch, through this second resistor and down to ground. And you'll notice that I'm now using the same convenient ground bus that I'd used earlier on constructing the analog circuit above. So with the switch in this position, I now have a complete circuit, and the voltage on the upper side of this resistor will be at 5 volts relative to 0 volts on ground right here. So if I take this green wire and connect it to pin number 2, which we've named switch 1, now I have a signal that I can send to the hero. When the switch is in the off position, the voltage on this green wire, and therefore on pin 2, is 0. And when the switch is in the on position, like so, now the voltage on the green wire, and which is sent to pin 2, is high, or 5 volts. And so the hero will be able to read that input and take appropriate actions on pin 12 and turn the LED on or off. By the way, there's a detail of our switch circuit that may bear a little explaining. And so let's dive into it in a little bit more detail. You may be wondering why we need to have a resistor between the switch and the hero board in our circuit. And perhaps the best way of explaining is to examine what would happen if we didn't have that resistor. So I'll direct your attention to this diagram that shows us what the circuit would look like if we tried to connect and disconnect 5 volts to our hero input with just a switch. So what we have here right now is a diagram that shows the switch in the open position. That is, 5 volts is not connected to the other side of the switch. In this case, you can see that the hero input, our input pin, is connected by wires directly to ground, that is, to 0 volts. And so there's no ambiguity there. The hero should see a signal of 0 volts or low when the switch is open. So that's not too surprising, and it would seem as though this would be a perfectly fine way to wire up the circuit. But now let's look at what happens if we close the switch. If we close the switch, we now have a sort of a strange situation because the hero's input is connected by wires both to 0 volts and to 5 volts. So what is the voltage recorded at the hero input? It's really not determinate because we can't really have this be at 2 different voltages. In fact, if we tried to do this, if we tried to connect 5 volts to ground without any resistor in between, the current that would flow would be huge. Probably more than the current that the hero can actually supply. This would be a short circuit. And it has the other undesirable effect of providing or producing a voltage here at the hero input pin, which is indeterminate. We just don't know what it would be. So this would be a poor way to design our circuit. It wouldn't work as we wish it to. So instead, what our solution is place a current limiting resistor, in this case a 220 ohm resistor, between the hero input and ground. You'll notice that in this state, with the switch open, we still have the hero measuring a voltage of 0 volts on its input. We can see that because we can see a path that connects from ground to the hero input. And since there is no current flowing, there is no voltage difference between the two sides of the resistor. It's 0 volts on this side, 0 volts on this side, and so the hero sees 0 volts. Now, unlike in the previous case when there was no resistor, when we close the switch, like so, we now have current flowing from 5 volts to ground through the 220 ohm resistor. The amount of current, if we wanted to know what that would be 5 volts divided by 220 ohms. The important point for us to note now, however, is that since there is a current flowing through this resistor, there's a difference in voltage between this side, which is connected directly to 0 volts or low, and the other side of the resistor, which is connected directly by wires to 5 volts. And we can see that our hero, there's now no ambiguity about what the voltage is on the hero input pin. It's 5 volts. And so we have exactly what we need. That is an input which is 0 volts when the switch is open and 5 volts or high when the switch is closed. And so that, in a nutshell, is why we want to design our switch circuit with a resistor in this position. So with that, I think we're ready to go ahead and try uploading our code and see if this will work as we've designed it to. So we have our code constructed. Let's go ahead and upload it to the hero. We would not expect anything to happen immediately because as we've set things up right now, the voltage on pin 2 is 0. It's low. And so that means that when we get to the conditional test, it's going to the second of the two choices, which is turn the LED off. So let's see what happens now if we take our switch and flip it to on. And there we go. We have now succeeded in remotely activating the circuit that illuminates the LED by providing a signal input into pin 2 of the hero. So this is yet another useful way of indirectly controlling the function of an analog circuit. And in this case, what we've had the hero do is make a decision based on inputs provided to its input pin. So that's a pretty helpful additional capability that we can now work into our subsequent projects and designs. If you were so inclined, you could elaborate on this and do some additional changes, make some additional functions if you wanted. For example, all we've done right here is simply caused the flipping of the switch to turn the light on and off, which is almost indistinguishable from if I were to just put the switch directly into the circuit itself. I could do something a little bit more interesting if, for example, I took the code that is executed here when the if statement is true, that is when switch 1 is high. If I replaced that digital write with a series of commands similar to those that we saw in our last session, so instead of just a single digital write, let's try this and figure out what it's doing. It's saying digital write LED low, wait for a second, digital write LED high, wait for 1/10 of a second, low, wait for 1/10 of a second, high, wait for 1/10 of a second, and then repeat. So it looks like what we're going to have now when we flip the switch on is a flashing sequence, where first we'll have the LED off for a second, then on for 1/10 of a second, off for 1/10 of a second, on again for 1/10 of a second, and then repeat. So it'll be a double fast flash followed by a long pause. So let's see if that works. Let's go ahead and re-upload our code. Once again, there's nothing happening until we flip our dip switch into the on position. And when we do that, we now have a function that we can control with a single flip of the switch, which will execute a more complicated sequence of flashes. So you can try doing some of your own experiments and modifications of this kind as you get used to controlling your lights, conserving your battery power, we hope, and start looking into some of the other parts of your rescue shuttle that are perhaps dark right now. And as we get more of the lights turned on and more of our functions going, we'll be ready to tackle some more challenging problems. The next time, I think we're going to try and control more than just a single circuit and try our hand at doing something even a little bit more complex. So go ahead and work on that. We'll continue watching telemetry here from Rescue Shuttle Control. And until next time, when we have our next session together, remember, invent safe.